Today we're doing the Atterberg Limits Lab. We're going to assess the behavior of fine-grained soils and determine the liquid and plastic limits. We can use these along with figure 2.13 in our textbook to classify fine-grained soils. When you get the keys to the lab, you also get the powers of teleportation, telekinesis, and you can also tell a lot of jokes. And now go in, say, whoop, and that's it. That's all.
Oh yeah, I like it.
John obviously has the keys to the lab, but he gave up his powers for his guitar collection. Now let's go through the equipment. First is the liquid limit machine and the Casa Grande grooving tool. The definition of the liquid limit is tied to this device. We have our lab datasheet and our pen so we can record the necessary information for both the liquid limit determination and the plastic limit determination. Today we'll be using this mystery soil. Here's our small spatula and ruler, our sample mixing bowls, our large sample bowl, deionized water, our paper towels, our 4 small sample tins, plastic limit plate, a reference 3mm wide rod, and our scale that is accurate to at least 1/100th of a gram. Before we begin, we must check that the drop height of the liquid limit machine is correct. For this test, the maximum height when it's rotated like this should be exactly 1 centimeter. We can conveniently use the bottom of the grooving tool to measure this. And we can see that our liquid limit machine is properly calibrated. Now let's measure some soil to mix our samples. In this demo, we want to show you the difference between the samples next to each other, so I'm going to use 4 small sample mixing bowls instead of just 1. However, I'm going to tare the scale with this bowl already on it so that I can measure the weight of the soil directly, and I'll measure out 400 grams of this soil as a repository to mix the other smaller samples. I'm pouring the soil into the bowl very carefully and very close to the bottom of the bowl. This soil is primarily fine-grained soil, so I'm being careful not to create too much dust. I'm going to take a couple scoops one at a time so that I can get a large enough sample to measure out 4 different smaller samples later. I just need to add a little bit more because we're almost at the 400 grams, and then we can add water and measure out our samples. Alright, now Heba's going to add some water, and we're going to see what happens when we add just a little bit of water to fine-grained soil. So we can see that we're adding just a few squirts of water here, and I'm going to go grab the camera so we can get a closer look. So we can see there's barely any water in here, and Heba's going to take the spatula and carefully try to mix it together as evenly as possible. But because there's not that much water in here, it's really difficult for her to mix. Even as she adds more and more water, it's still very difficult to mix, and we can see the soil begins to clump up. You can see that as she adds water and mixes the soil together, there's some gravel-sized particles that we know won't pass the number 4 sieve. So that's not very good for sieve analysis. Luckily, we're doing Atterberg limits. I'm going to take what's in this bowl and I'm just going to practice my telekinesis, and now we have 4 sample bowls of different water contents. The first bowl is the lightest color and has the most water in it, and it's very easy to use the spatula to move. The second bowl, you can still use the spatula to move and cause indentations, much more than the third bowl, which is darker in color and harder to spread. The fourth bowl is used for the plastic limit determination. It's going to be the stiffest of the bunch. We will use 4 small sample tins, numbered so we know which one corresponds to which test. We have 3 tins for each individual liquid limit test, and 1 for a combined plastic limit sample. We'll record the weights of each empty tin on this sheet. We realized that we actually need a pen, so I'm gonna go get one for Heba, and when I do this, I'm going to make John disappear, so make sure you watch very carefully because this is super important and you wouldn't want to miss it. So now John's gone and we can weigh the empty sample tins on our scale, which is the right scale, and I bet you didn't even notice that we had the wrong scale again. Misdirection. This scale is literally the bane of my existence. So now we can actually weigh and record each of the sample tins. Now Heba's going to take our first and stiffest soil sample and spread it into the liquid limit bowl. It's important to do this evenly through the bottom half of the bowl, and it shouldn't be too thick or too thin. In the ASTM procedure, we would start by running the test on the soil with the lowest water content, and slowly add more and more water to the sample for each test in the small sample bowls. This gives the person doing the tests more control, and they can more easily tell where they are in relation to the elusive 25 blows. We use the standard Casa Grande grooving tool to make our groove all the way down the sample at the standard width. The Casa Grande grooving tool is super useful throughout the test, but I'm not going to tell you all of the uses until later, so you have to actually watch the video. After making sure the automatic counter is set to 0, we can begin the liquid limit test. Heba will rotate the handle so that the bowl of the machine is dropped to the 1 centimeter at about 120 beats per minute, which is approximately the same rate as CPR. We can see the groove of the soil, and we will run this test until it is closed ½ an inch. Heba can hold up the grooving tool to compare for the closure. This is another one of the neat features of the grooving tool. See that after 36 blows, the groove is closed ½ an inch. After the test, we take a sample from right where the gap closed, and then we want to scoop it out with the spatula to save as much of the soil sample as possible. We want to clean the liquid limit device with a paper towel between each trial so that it's clean for the next use. Now we're going to do it all again on the next soil sample. This soil sample is more wet, so it should take fewer blows to close the gap. You can see that it sticks more to the spatula, and as she evenly spreads it through the lower half of the liquid limit device, it looks like it holds its shape more. The Casa Grande grooving tool is used a lot in this test. It creates a groove that is 2 mm wide at the base of the liquid limit bowl, and when held perpendicularly, ensures that the soil is the right thickness in the bowl. We can see the brass at the bottom of the groove through the whole liquid limit bowl. But at the 27th blow, the gap closes all at once. Ebba compares the bottom of the grooving tool to the gap closure in the bowl. You can see that more than half of an inch has closed since it happened all at once. But before it closed, it hadn't reached the required half an inch, so we marked this as 27 blows.
Using the wettest sample, I'm going to carefully spread it into the lower half of the liquid limit machine. I want to be careful to get it evenly spread to about the depth of the grooving tool all the way across the lower half of the bowl. I am going to center the grooving tool and then, keeping it perpendicular to the bowl, I'm going to scrape it down the bowl. No more than 3 mm of the soil should be trimmed off the top with the grooving tool. I'll make sure the blow counter is 0 before I begin. Now I'll rotate the handle so that the bowl is dropped at 120 rounds per minute until a section of 12.7 mm, which is half an inch, along the groove is closed. The Casa Grande grooving tool can be used to compare. After 14 blows, this sample reaches the defined state. You can see how the groove has closed in this lower section of the bowl at 14 blows.
Now we can weigh and record the weights of the sample tins with the samples that we got from each of the liquid limit tests in it. And this will conclude the liquid limit section of the experiment. Now we can start the plastic limit test, and I'm going to take our most stiff sample with the least amount of water, and I'm going to take a pea-sized chunk of that, and I'm going to start rolling it out on our plastic limit plate. The key of this test is that I want to roll out a sample of soil that is 3 mm in diameter before it begins to slightly start cracking. We compare with this 3 mm wire gauge, and that's how we can see that this is 3 mm, but it hasn't started cracking yet, so it's still too wet to be at the plastic limit. I'm going to take this same sample and I'm going to roll it around in my hands a little bit to try and dry it out and get some of the water on my gloves and on the plate to see if maybe this will be the plastic limit. I'm really not very good at the plastic limit test.
It's too dry, it's too dry. Oh my god, it's crumbling. It's crumbling.
And we can see here that this time the soil sample is too dry and it's crumbling before it reaches the 3 mm mark. This means that the moisture content is too low, so I'm going to grab another sample and try again. But this one rolled smoothly past the 3 mm mark, so I'm going to try to dry it out yet again and see if that works.
Oh my god, it's crumbling. Oh my god.
This time I'm going to try a new technique. I'm pretty confident that it's going to work out.
I think what we're going to need to do is we're going to need to have cover through this. Because it just crumbled. Okay.
I'm going to fix my glove and...
I'm going to take over for Alyssa now. This time I'm going to take one large sample and cut it into pieces using the spatula. This way, the sample I start with will still be peanut sized. I'm going to start rolling gently to get a feel for the consistency. I just watched Alyssa do this, but I still need to calibrate myself. And this sample just keeps rolling. Since it's approaching 3 millimeters, and we can see that it isn't crumpling, the water content is too high. So I'll use a slightly smaller sample and try to dry it out before I begin. Rolling it out, I can see it's still too wet. You can see it also stays together when I pick it up. Take 3. This one rolls way past 3 millimeters. Look how thin it is. This time I'm going to make it dry out by rolling it in my hands more before starting. I roll it around on the plate before I begin to roll it out too. Yay, it's cracking! Come take a closer look. We can see that it's 3 millimeters now by comparing it to our handy dandy rod. And we can see that it's just beginning to crack, which is how we define the plastic one. So I'm going to take this sample and put it in the 23 cup. Now that I have gotten a feel for the right consistency, I can redo this to add another sample to the tin. This sample again begins to crack just as I approach 3 millimeters. Now you can try again, Alyssa, since I just showed you how to do it.
All right, take two. There we go, crack, 3 millimeters.
Oh,
Look at that, look at that. That's cracking. For sure. Oh, cracked.
okay. Now we can take the tin with all 3 samples in it and weight it.
Now we're going to take all 4 of our soil samples into the oven, and this way we're going to get to dry them out, and we can weigh the weight of the dry soil in the tin in order to measure the water content. And we can see we put the soil samples in at 10 past whatever, so we'll come back in 24 hours to weigh them once they've fully dried. Now that it's been 24 hours, we're going to take the soil samples out of the oven. Heba's going to wear a protective glove to take the soil samples out because the metal containers are going to be very hot. The last step is to weigh and record all of the soil samples again with the weight of the dry soil in the can. Then we can use this information to calculate the liquid limit and plastic limit, and then we can classify the fine grained soil.
So let's move to the data analysis part. You'll have 2 tables, one for the liquid limit determination and the other for the plastic limit determination. For the liquid limit part, during the lab you'll be able to record the can number, the weight of the can plus the wet soil, the weight of the can plus dry soil, and the corresponding number of blows. You should be able to have 4 samples, with blow counts between 30 to 35 blows for the first sample, 25 to 30 blows for the second sample, 20 to 25 blows for the third sample, and 15 to 20 blows for the fourth sample. Due to time constraints of the lab, you'll probably be able to have only 3 samples as shown. In order to get the liquid limit, which is the water content corresponding to 25 blows, we need to plot the water content versus the number of blows on a semi-low scale. The water content represents the ratio between the weight of moisture to the weight of dry soil. First, let's calculate the weight of dry soil by subtracting the weight of the can from the weight of the can plus dry soil. Next, let's calculate the weight of the moisture. by subtracting the weight of the can plus dry soil from the weight of the can plus wet soil. Afterwards, we can calculate the water content by dividing both values, the weight of moisture by the weight of dry soil. Now we can plot the water content versus the number of blows data points. You should be able to choose a proper fit for the data points you have, which is known as the flow curve. It should be slightly curved, but you can approximately consider it a straight line. You should use the straight line to get the water content corresponding to 25 blows, which is considered the liquid. Let's move to the plastic limit part. You'll have the same measurements recorded for the plastic limit sample. You'll need to calculate the water content for the sample, which represents the plastic limit. So again, we are going to calculate the weight of dry soil and the weight of moisture and divide the weight of moisture by the weight of dry soil to get the water content. To sum up, your report should include a plot for the blows versus the water content on a semi-log scale. You should be able to calculate the liquid limit, the plastic limit, the plasticity index, and the flow index. And you should be able to provide a general classification of the soil and check whether that agrees with the visual observations or not.